So thank you very much for inviting me. I'm thrilled to be on a conference for the first time since almost 2 years, since actually end of March of 2020. I'll talk today about, basically it's a project more than I will formulate several theorems, but it's more like a project, an attempt to study Alfor's regular conformal dimension using group theory. So how could that be achieved? So let me start from the setting. So the setting is a covering map where, so this is a covering map where M is a compact metrizable space or a metric space. The metric is not very important here. Yeah, it will be important. And such that it's locally expanding in the sense that there exist constants epsilon greater than 0 and L greater than 1, such that distance from f of x to f of y is greater than L times distance from x to y for all x, y in M of such that distance between them is less than epsilon. So an example of this would be a hyperbolic complex rational map restricted to the Julia set. So you will have then this expansion condition for the restriction of the Poincare metric. And many other examples. Say a class of examples where M is a manifold are precisely when M is an infranil manifold, so when it's a quotient of a nilpotent Lie group by a discrete affine group, and F is induced by an expanding automorphism of the Lie group. So now I want to associate an algebraic object with this situation. And for that, I will assume that M is path connected, though it's not really needed. It's just easier notationally, but everything what I say will be true for any expanding map, a covering map. So if you have a point in M, 2 points in M, T1, T2, and a path L from T1 to T2, then you can lift this path using the map F. And so T1 will have some preimages, T2 will have some preimages. So if you take this path L, you can lift it, and you will get a bijection between the preimages and the F. Then these preimages will have preimages. You can lift the lifts, and you'll get bijection between, well, between these preimages and so on. If you take the union of all of this, you can think you will get a bijection between the backward iteration, so preimages under iterations of F to preimages under iterations of F of T2. So this is arranged naturally into a tree, which I will denote Tt1. These also form a tree, Tt2, and we get an isomorphism of these trees, which I will denote SL. And you can look at the boundary of this tree, of these trees. So boundaries are Cantor sets of all paths, infinite paths going infinity, and this isomorphism of trees will define a homomorphism of the boundaries of the tree, of the trees. And we obviously have actually kind of an action of the fundamental groupoid on these boundaries of the trees. So if you take one path and then continue it, the corresponding the isomorphism induced by concatenation of the paths is the same as composition of the isomorphism induced by each of the paths. In particular, if we fix a point, if you take one point T, then we have a semigroup of partial isomorphisms of subtrees of this tree, defined by paths connecting different vertices of this tree. So take two vertices of this tree. So we have the tree. Let's take the case when degree is 2. So we have a binary tree, rooted tree. And then for any path inside M from one point to another, when we lift these paths, we'll get an isomorphism from this tree to this tree. So we get, on the boundary of the tree, we'll get a homomorphism between a clopin subset of that boundary and another clopin subset of that boundary. And the set of such homomorphisms will be what is called an inverse semigroup. So it's not a group because homomorphisms are not defined on the whole Cantor set, the whole boundary of the tree, but it's a set of homomorphisms between clopin sets, and this set of homomorphisms is closed under taking inverse and composition, though composition is a composition of partial maps, so sometimes you can get empty map and so on, but it's something that algebraists call an inverse semigroup. And this inverse semigroup is finitely generated. So I didn't claim that M is locally simply connected, but it doesn't matter. Well, let's pretend that it is for a minute. Then the fundamental group will be finitely generated. So this semigroup will be generated by the generating set of the fundamental group and any collection of paths connecting the base point to the immediate preimages. So if you take these paths, this inverse semigroup will be generated by these paths, by the corresponding automorphisms of the tree. So there will be some automorphisms of the tree, and then partial automorphisms which map the whole tree to this subtree and whole tree to this subtree. The semigroup will be generated by these. Even if the space is not locally simply connected, the set of automorphisms that you get from the loops will be still finitely generated because of the expansion. The fact is that any loop which is small, sufficiently small, when lifted, will be definitely a loop even smaller, and so on. So all small loops act trivially on this tree. So even if the space is not locally simply connected, the group is still finitely generated. The group defined by loops, the subgroup defined by loops in this semigroup will be still finitely generated. So the group defined by the loops is called the iterated monodromy group of the map F. But in addition to iterated monodromy group, we have these maps which map the whole tree to subtrees. But now this group, the iterated monodromy group, so we have the group, the iterated monodromy group, the subgroup of this semigroup generated by the loops. And as I said, there are additional generators, which in the case of degree 2, there are 2 additional generators, which map the whole tree to the subtree growing from the first level. So let's denote the set of those additional generators by X. And then for every element of the iterated monodromy group, so for every loop, and for every element of this additional generating set, so for every path connecting the base point to a preimage, we'll have the following relation, that if you apply Sx and then I compose them this way, and sorry, if you apply Sg and then Sx, you can rewrite it as applying, sorry, I confused the sides again. If you apply Sx and then Sg, that will be the same as applying some Sy and then Sh. So for all g and x, there will exist h in g and y in x, such that the following relation holds in our semigroup. Namely, what are these? So in the semigroup that I just mentioned, the semigroup of all these homomorph. So the question was if where this relation holds. It holds in the semigroup of those partial isomorphism between subtrees defined by paths. Let me explain it. Since I see inverse semigroup, I can rewrite it in a different way. So if you take, so this is our path G, this is our path X, and so what are these H and Y? So this is a path in the base point. This is a preimage of the base point, so we can lift this path G in a unique way, and this by the map F, by the covering. So the map F acts like this. It maps both these points to the base point. So this is a lift, and this is one of the preimages, immediate preimages. So there is an element of X connecting it to the base point, and that element is our Y. And our H will be this triangle. So you go along X, then along this lift. Let's denote the lift by Gx. So the relation will be that yes, so H will be the concatenation of the paths X, Gx, and then Y. Why this is so? Because just from the definitions, if you take these three paths, the corresponding automorphism, the corresponding element of the semigroup. So if you take this path, the corresponding element of the semigroup will be Sx, Sgx, and then Sy inverse, or y inverse. And by definition of Gx, by definition of G, G is the Sg. Sg is the automorphism of the tree defined by G. So it's defined by lifts of G everywhere. So restriction of this Sg to the subtree starting in this vertex is exactly, so if you restrict it to the subtree starting in this vertex, let's call it Tx, then this is exactly Sgx. Because by definition, Sg is defined by taking lifts of the path G everywhere. So it's the isomorphism between the trees defined by these lifts of Sg. One of these lifts is Gx. So if you start lifting Gx, you get the same isomorphism, but you started only from this vertex. You didn't start from the root of the tree. So you have your binary tree describing the action of F, and Sg is the automorphism of this tree induced by defined by lifting the path G. But now if you restrict it to this subtree, it will be this map is defined by lifting this preimage of G to this subtree. And so restriction of Sg to this subtree is exactly Sgx. And you can check that this is exactly what it should be. Yes, essentially this is what I wrote here. So here what we do, we map the whole tree to this subtree and then apply Sg, but applying Sg is the same in this case would be as applying restriction of Sg to this vertex, so it's applying Gx, and then we come back using Y. And so you can check, one can check that you have this relation. Okay, so what we get here is, so let me give you an example of such computation. So for example, if you take z square minus 1 rest of the basilica, you will have two generators of the iterated monodromy group, A and B. I just want to show you how these relations here, and then there will be two elements of the set X. So if you have a base point, it will have two preimages. So let's take the base point. So these elements A and B will be defined by loops going around two postcritical sets, two postcritical points, 0 and -1. And if you take the base point, it will have two preimages. Let's say take the base point, the fixed point between 0 and 1. So it will have two preimages. And let's take one connecting path, the trivial one, denoted x0, and another one, the non-trivial one, denoted x1. And then one can show that, so if you take A to be the loop around critical value and B a loop around 0, in that semigroup you will get that SA, if you do S x0 and then XA, it will be S x1 and identity. Because if you lift A, you will get two curves like this. And so if you do first, if you do x0, then you take the lift of A will be this path, and then you come back in that triangle using the connecting path, you will get a trivial path. So it's this relation will give you this relation, and then you can check that this is this relation, and then for B you will get these relations. So it's annoying to write these S's, so we'll just write it this way. A x0 is x1, A x1 is x0b, B x0 is x0, B x1 is x1a. And this is something that was known in group theory as a self-similar group for a biset. Namely, if you take any product of these x's, xi1, xi2, xin, and multiply by A, you can use these formulas to rewrite it. So you have A times x something, x0, x1. You can rewrite it now as xj1 times some group element, times another group element, well, a generator A or B or identity. Then again, you can rewrite this using the same formulas. Again, you can switch letter and group element, this x and a generator of the group, and rewrite it again as some other letter and some other element of the group.
Could I ask a quick question? So can you hear me?
Yeah.
Just to clarify, so the x0, so let's say your base point is the alpha fixed point, then your x0.
In this case, is the trivial path. Yeah.
No, just the x1 and the x0 to begin with. So just you're connecting your base point to the preimage of the alpha fixed point. One's on the top and one's on the bottom or something. That's your x0 and your x1?
Yes.
Okay.
So X is, so the whole semigroup is generated by two sets, by union of two sets. One set is the generating set of the fundamental group, for example, and the other set is the set of connecting paths from the base point to immediate preimages of the base point. Yeah, it's clear? Did I answer the question?
Yes, thank you. Sorry, I just realized my video was off. Sorry.
Yeah, we can take the fixed point between 0 and -1 of Basilica, which is what? I forgot. But this square -1 will have two preimages, how are they called? Alpha and beta, and that's the beta one. This is alpha one, okay. Not the landing point of ray 0, but the other one of landing. No. Yeah, so I take this. This is called alpha, the one which has two rays. Yeah, so you take alpha and minus alpha. Sorry, I thought that you say that minus alpha is a fixed point. No, correct. Alpha and minus alpha, yeah. So x0 is the trivial path at alpha, because alpha is preimage of itself, so we can take the trivial path as the connecting path, and then you take x1 is this path in the upper half plane from alpha to minus alpha. Did I? In these formulas? Okay, I'm sorry for that. Yeah, I'll change this. Thank you. Okay, so we get these can be seen as some kind of rewriting rules that allow us to write any product, an element of the fundamental group times a product of these x's to product of these x's times an element of the fundamental group. So, and this is exactly what is a self-similar group. Now this inverse semigroup, which I mentioned at the beginning, it's a semigroup of partial homomorphisms, so of the boundary of the tree. So it's a semigroup of homomorphisms between Clopin sets of the boundary. In fact, it's more natural. So this semigroup is nice. It's given by finite number of kind of defining relations, which I wrote above there. But okay, sorry. So let me repeat one more time what I wrote at the end there. So we have self-similar group, which means that so there is the iterated monodromy group, the subgroup of this semigroup, which is defined by elements consisting of elements defined by loops. Then there is this set of paths connecting the base point to the preimages. And in this semigroup, we have relations of the form that if you take any element G in this subgroup, and you take any element V in the semigroup generated by this set of connecting paths, so all products of these elements xi, then there will exist a unique element H of the group and a unique element U of this semigroup generated by X, such that G times V is U times H. So you can rewrite, and actually it's easy to write it explicitly what it is. So this V is a product of these isomorphisms of the whole tree with the subtree of the first level. And so when you compose two of such, you will get an isomorphism of the whole tree with the subtree of the second level. And so on. If you compose n such, you will get an isomorphism of the whole tree with a subtree of the nth level. So it will be defined by a path connecting the base point to that point of the nth level. So there will be some path L1 connecting the base point to that point of the nth level. And then G will be a loop. So you can lift this loop to that point of the nth level, so to nth preimage, by nth iterate of f. So that will be your lift of G. And then there will be one path corresponding to V. And there will be a unique path such that the corresponding isomorphism of trees will map the whole tree to the subtree of nth level. So that's your L2. And that L2 will correspond to U. And then H will correspond to concatenation of these paths. In particular, you see that because we assume that our map is expanding, this lift will become shorter and shorter. And this can be used to prove that eventually these elements H, these triangles, these concatenations, will belong to one fixed finite subset of our iterated monodromy group. So there will exist a unique finite subset of the iterated monodromy group, so of the subgroup of our semigroup generated by loops, such that when you do this rewriting, so when you're lifting paths and completing these paths by the connecting paths, you will reach the set n. So for every group element, there will exist n such that for every v in x star of length n or more, let me denote this element h by g with index v. This g with index v, so this element which you get over here belongs to this finite set. And such groups are called contracting self-similar groups. Such iterated monodromy groups. Contracting self-similar groups. And this is an algebraic characterization, like algebraic counterpart of expanding covering maps. That conversely, every contracting self-similar group, so every group given by relations like above there, for Basilica, which satisfies this condition, appears in this construction. So it is iterated monodromy group of some expanding map. With one caveat, you have to consider Orbi spaces, like you have to include subhyperbolic cases here. And that's a little bit technical in this case. But modulo this technicality, you have a complete like a bijection between expanding covering maps, modulo topological conjugacy, and contracting self-similar groups modulo some type of algebraic equivalence, which is also a little bit non-trivial, but can be easily formulated. So we have an algebraic theory in this way. We get an algebraic theory of expanding covering maps. In particular, this implies that there are only countably many of them up to topological conjugacy. That's one of proofs that you can use. So how you can reconstruct from this semigroup this expanding map? So the idea is very similar to the idea of Gromov hyperbolic groups and boundaries of Gromov hyperbolic group. In a sense, this semigroup should be thought of as a Gromov hyperbolic group, even though it's not hyperbolic and not a group. I mean, it is not a group, but it is hyperbolic. So let me explain you how it is hyperbolic. So if you have a group, you draw the Kelly graph, and it's negatively curved, and then the boundary is the space that you're interested in. Here, the Kelly graph of the semigroup is not what you should think about. What you should think about is the Kelly graph of the associated groupoid of germs. So you have this semigroup acts on the boundary of the tree. So it's a group of partial homomorphisms of the boundary of the tree, of the boundary of preimages. So you can look at germs of this semigroup, germs of its action on the boundary. So you take a point on the boundary. So you have your tree of preimages. It has your boundary. It has the boundary. And then you pick some point of that boundary. So pick some backward orbit. So let's call it Xi. And then take your generating set of this semigroup. And then for every element of the semigroup, you have the corresponding germ. If that element is defined on Xi, you have your element as defined by some path L. It acts on some Clopin set. And if that Clopin set contains Xi, you have the germ of the action. So you identify two semigroup elements if they act the same way around this point Xi. And then you draw the Kelly graph. So among these germs, if you have one germ and another germ, so the germs will be vertices of your Kelly graph. And you connect one germ to another if you have a generator such that this germ is composition of this germ and the germ of the generator. So it's exactly the same as for Kelly graphs of groups. The only difference is that you have to fix a point and look at germs of this group at a point. If you have a group action, you will get every element will be defined on this point. So these germs will come from group elements, and every element will have the germ at that point, and it will be closely related to the Kelly graph of the group. In this case, there are many elements of the semigroup which are not defined on Xi. You ignore them. So how will this graph look like in our case? So in our case, our generating set is split into two parts. There is the generating set coming from loops and the generating set coming from connecting base point to immediate preimages. And so the edges of the Kelly graph will be also split in two parts. There will be edges which correspond to loops, and edges corresponding to the connecting paths. And it's natural to draw edges corresponding to groups kind of horizontally, edges corresponding to connecting paths vertically. If you take the vertical part of the Kelly graph, you will get a regular tree. So for example, in degree 2, you will get a tree which has one edge going down and two edges going up all the time. So these are our x's. x0, x1, x0, x1, x0, x1, and so on. The edges corresponding to loops, so generators of the iterated monodromy group, they will connect these vertices horizontally. So in this tree, they will, because the loops will preserve the levels on the tree, you will get some connections horizontally. So in each level of this tree, there will be some horizontal edges. We'll get this infinite graph, which is naturally graded by this subtree corresponding to the set X, to these connecting paths. And edges are either these connecting paths arranged into a tree or some horizontal paths connecting these vertices of the same level. And the fact is that this graph, so let me denote this graph by gamma, it depends on Xi. This graph is Gromov hyperbolic. So that's what I meant when I said that this is a hyperbolic semigroup in a way. But it's not just this graph has a special point on the boundary corresponding to going down in this tree. So the boundary has a favorite point. Let me call it omega psi. And then we have the Gromov boundary. And it's natural to remove that point, because then the boundary will correspond to going up in this tree. And it will be a non-compact space kind of completing this tree upstairs. So it will be like a upper half-plane model of the hyperbolic plane. So there is a special point, and then there is the real kind of real line. And so what is that space? What is that boundary? So remember, psi is an inverse, or is a point of the boundary. So it's an inverse orbit of T. You choose each time one preimage. So this boundary will be a leaf of the natural extension of the covering. So if you have our covering map F, we can look at the inverse image, the projective limit, the inverse limit of iterations of F. And then it is naturally a fiber bundle where fibers are the boundaries of these trees that I was talking about. And base is M. And so in that fiber bundle horizontally, you get leaves. In the case when M is path connected, those leaves are exactly the path connected components of the inverse limit. And psi corresponds to one point of the inverse limit. And then this boundary is exactly the connected component, the component corresponding to that point. More precisely, if let's M hat will be the inverse limit of these spaces, then F induces a homeomorphism of this inverse limit. It's called the natural extension. And this natural extension is a hyperbolic dynamical system. So there are stable and unstable equivalence classes. And this boundary of this Gromov hyperbolic graph is the unstable equivalence class of the point psi. So it's, yeah. OK, so now, yeah. Yes. Mm-hmm. No. Yes. 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 What were you saying? So the Cantor sets in the if you take the Basilica natural extension of Basilica, the Cantor sets are the stable equivalence classes. So if you take 2 points in that Cantor set and iterate your natural extension, they will converge. The distances will go to 0. Now, if you take the inverse map, then the set you have the unstable equivalence relation. So it's the pairs of points where distances go to 0 if you take the inverse map. So these equivalence classes, the unstable equivalence classes, are exactly the boundaries of these graphs. And they are exactly the path-connected components of that bundle. The path-connected components with a natural inductive limit topology. So when you unwrap it. OK, so let me go. OK, sorry. So this is a particular case of a more general setting of so-called hyperbolic groupoids. So that includes many more examples, not only coming from expanding maps. And in all these cases, the Kelly graphs have this, the Kelly graph of these hyperbolic groupoids, they have this special point on the boundary. And so they are also stratified like this by horocycles corresponding to that special point. So these levels of the trees are the horocycles corresponding to the, horospheres corresponding to this point on the boundary. And we have the levels. So the levels can be described using the Busemann co-cycle. The Boseman co-cycle in this case, it just measures the difference between the levels of this on this graph. So we have, if you take any germ of, if you take two germs, then you can close this diagram. So you get another germ closing the diagram, and the value of this co-cycle on this germ. So if let this germ be gamma, the Boseman co-cycle beta of gamma is just the difference of levels. The level of the end of the germ minus the level, well, it's positive if you go up, and take the difference between these levels. So that's the classical Boseman co-cycle for a hyperbolic graph associated with a point on the boundary. But that's not the only one Boseman co-cycle, because if you forget where this graph came from, you look only at quasi-isometry class of this graph. You just remember this graph up to quasi-isometry, and you remember this special point. There will be many Boseman co-cycles associated with each realization of this graph in the quasi-isometry class. So let me give you a general definition, and then I will, in the remaining 10 minutes, talk about how it is related to the dimension. So let G be a topological groupoid of germs of some semigroup. So in our case, we have a semigroup. It consists of homeomorphisms. You take germs of these homeomorphisms, and the topology is natural. If you have some partial homomorphism, then germs of these partial homomorphisms, the set of germs of these partial homomorphisms is homomorphic to the domain. So you have your homomorphism, it's a bunch of germs, and this bunch of germs has the same topology as either domain or range. So you get if you have a semigroup of local homomorphisms, that defines a topological groupoid, so the set of these germs. And then a quasi-Co-cycle on G is a map beta from G to R such that there exists epsilon, or not epsilon, eta greater than 0, such that first, this is almost continuous in the sense that for every germ gamma, there exists a neighborhood U of gamma such that the values of beta vary at most by eta for all elements of this neighborhood. And the co-cycle property is that for all composable germs, gamma 1, gamma 2, you have the product gamma 2 of gamma 1, beta of gamma 2, gamma 1 minus beta of gamma 2 plus beta of gamma 1 is less than eta. So it's almost additive and it's almost continuous. So an example is, well, where eta is 0 actually, is that co-cycle coming from those graphs. So for the semigroup which I was talking about today, you look how the germ how much you change the level, from which level you go to which level. That's an integer. And it's continuous, it's locally constant actually. And if you go up or down, you add the differences. So that's a continuous, that's an honest continuous cocycle. Here's another example, which is kind of dual. Yeah? Sorry? Yeah, I know. So here's another example. You take F to be the groupoid of germs defined, generated by F. F is a local homomorphism, so its germs are invertible. So you can generate a semigroup of local homomorphisms by F. That will give you a groupoid of germs, and there are two natural choices. So every element of this groupoid looks like that, like this. You take a point, because it's Z, you apply F some number of times, and then you apply branches of F inverse some number of times. So if you compose F and then F inverse, that will be a germ in this groupoid, and all elements of this groupoid are like that. So you go n times here and say m times here, so you can define the value of the germ of the Boseman cocycle as say m minus n, for example. Then this will be a cocycle. If I did it right order, if you draw the Cayley graph of the graphs of the Cayley graphs same way as we did over there, they will be exactly trees without any horizontal edges. And this Boseman cocycle is just the degree, the difference of the levels. But suppose that F is an expanding map on, say, it's a, for example, it is a rational function. Then another choice would be to take logarithm, well, negative logarithm of the absolute value of the derivative at your point, at your base point. So this is point Z at point Z. Then this is also a cocycle, and it is also a Boseman cocycle for the same graph, but for a different realization, for different lengths of edges. So in the same quasi-isometry class, you have these two cocycles. Okay, unfortunately, I don't have time to tell what to say what I wanted to say, all what I wanted to say. So let me finish now by formulating some statements, and that will be it. So the point is that these two pictures are dual to each other. This groupoid and this groupoid, in the sense that, okay, let me. So if you have a Boseman quasi-cocycle on the, so we have two groupoids. One groupoid is what I defined at the beginning of the lecture, the groupoid defined by path. Another groupoid is groupoid of germs of this groupoid of germs generated by the expanding maps. And if you have better Boseman cocycle on G, then it can be in a unique way up to bounded additive constant associated with a Boseman cocycle on the natural extension. So it induces a Boseman cocycle, well, sorry, a cocycle on the groupoid generated by the natural extension. And then this cocycle induces a Boseman cocycle on the other groupoid. So if you start from a Boseman cocycle on a Cayley graph of one groupoid, through the natural extension, you get a dual Boseman cocycle on the other groupoid. So if you start from the derivative, for example, for rational function, you get a cocycle on the groupoid for the self-similar group. So the project which I mentioned is to study Boseman cocycles on self-similar groups. And each Boseman cocycle on this self-similar group will define a measure on the Julia set, so on the Gromov hyperbolic boundary, and a class of metrics. So if you have a Boseman cocycle beta, then it associates the visual metric. So and this visual metric exists starting from some exponent, and you have the measure, basically the Patterson-Sullivan measure associated with this Boseman cocycle. So this Boseman cocycle will be, for the measure, the Radon-Nikodym derivative will be exponent of this Boseman cocycle with some coefficient, and the visual metric will be the expanding map will be a similarity with some coefficient, with some derivative. And the logarithm of the derivative will be this Boseman cocycle with some coefficient. So you can associate with each Boseman cocycle its Hausdorff dimension. So that's minimum, the minimum of the Hausdorff dimensions of the visual metric. And one can associate then the smallest such Hausdorff dimension, which will be the Alfors regular conformal dimension. And one last quick theorem is the following. So I mentioned that these self-similar iterative monodromy groups are contracting. And contracting means that, as I probably raised that definition already, that these elements belong to a finite set. And that can be in a different way formulated as contraction of length. So if you have a group element and you take its length in the generating set, if you look at how this group elements acts on the subtree, so you look at these GV for some fixed level V, level N, you take all of them. So take all these elements, if you remember, they were defined by triangles of paths. And you take the vector of lengths of all these elements. So you take length of all these restrictions on that level, x to the n. This is a vector in R to x to the n, actually in Z. And you look how much the LP length. So you take the norm, the LP norm of this vector, and you look how much the LP norm is contracted. And you take the exponential contraction rate of this LP norm. So for being contracting is equivalent for L infinity norm to be contracted. And then there will be a critical value of P for which you still have contraction. And the theorem is that this critical value is very interesting. By the way, I include here also P less than 1. Theorem is that the Alfors regular conformal dimension of M is greater or equal to the critical value of P for which G is LP contracting. Okay, so I'm done. So the project is to study these Boseman cocycles and LP contractions, also similar groups, which are purely algebraic objects, and to apply it to the corresponding expanding map. That's it.
Thank you very much. Let's thank the speaker. So we have time for some quick questions. Any? Wait, Felix.
I think your measures via this graph are somehow related with coding, geometric coding. Your graphs are related to geometric coding trees. I developed a theory and transport of measure from symbolic space to.
Yes, yes. So this, yeah.
My another remark would be that there is another graph, but maybe it's very similar to yours by Pilgrim and Hajshinsky.
It is the same graph. I mean, kind of, my graph is a covering graph of their graph. Yeah.
Another visual measure.
Yeah.
Okay.
It is related to their work, yes. I should have mentioned that, of course. Yeah.
So in the case of the rational map, so we have this three-dimensional hyperbolic spaces attached to the ellipse of the natural extension, and I guess your Kelly graph for the groupoid is some discrete object, quasi-isometric,
yes,
to this hyperbolic spaces.
That's right. Yeah.
And so if you consider a general situation, so expanding map, do you have, well, you mentioned that you can also consider one-dimensional extensions of the unstable leaves. You have a natural hyperbolic structure there too, which is...
Yeah, but it's only discrete. Only, like, I mean, I have only graphs. I don't have any three-dimensional.
There is no sort of intrinsic good structure.
Well, it is up to quasi-isometry. It's a unique structure, but it's like a general case of general Gromov hyperbolic groups that you don't have any manifolds, things like that.
I see. So the only way to get it through the Kelly graph?
Yeah.
What about the upper bound for the alpha-spheroidal conformal dimension? Do you have anything to say about this?
So it's not. So this can be less than 1. So in the cases when M is topologically one-dimensional. So the inequality can be strict, but the only cases when it's strict is subhyperbolic cases which with really weird orbispaces. Like for the Grigor-Chu group, this number is exactly the number which appears in the growth of the Grigor-Chu group. So it's really interesting, when do we have a strict inequality here? And so this is the, like, maybe actually in the expanding case, not subhyperbolic, but when you really have an expansion, the way I defined it, maybe we have equality here, but I don't know.
I had a question.
Yeah.
So you defined, I think you defined what is a quasi-co-cycle.
Yeah.
But then you were also speaking about a Busemann co-cycle.
Yes. So in these 4 hyperbolic groupoids, if you have a hyperbolic groupoid like these 2 examples, G and F, for each of these hyperbolic groupoids, there in the Kelly graph there is a special point on the boundary, and then you define one has to consider a special class of quasi-co-cycles, which I call Busemann quasi-co-cycles, related to that point on the boundary. For example, in the case of the Gromov hyperbolic groups, Busemann co-cycle is a quasi-co-cycle. Always, there is also always this error. And so inside this class of quasi-co-cycles, so I gave definition what is a quasi-co-cycles, but I didn't give a definition what is a Busemann quasi-co-cycle. So it's some special type of co-cycles associated with hyperbolic groupoids.
Okay, thank you.
Any more questions in the room or remote? Okay, so then let's thank the speaker again